Lesson 6.7 is problem solving. When you are creating graphs based on tables of values or real world problems, you need to be able to look for symmetry. Symmetry is a really important part of graphing sinusoidals, and it really will help you. Here's our example, our only example today. The volume of air in the lungs during normal breathing is a sinusoidal function of time. Suppose a person's lungs contain from 2,200 milliliters to 2,800 milliliters of air during normal breathing. So imagine you're breathing air coming in, air going out. Suppose a normal breath takes 4 seconds, and at that time t equals 0 corresponds to a minimum volume. And the first thing we're going to do is let V milliliters represent the volume of air in a person's lungs, and we're going to draw a graph with V. So word problems, all that stuff I just read to you, you probably found it a little bit confusing. One of the best strategies for word problems is to read one sentence at a time. So let's just start with the first sentence again. The volume of air in the lungs during normal breathing is a sinusoidal function of time. Okay, that's interesting, but doesn't really have anything to do with our question. The next thing, suppose a person's lungs contain from 2,200 milliliters to 2,800 milliliters of air during normal breathing. So there we have some numbers. What are those numbers? Well, those numbers you're given are a max and a min. So let's label that. The first number is the minimum, and the second number is a maximum. So that's helpful. And then the next clue we kind of have here is a normal breath takes 4 seconds, and T equals 0 is minimum volume. So that's all important too. 4 seconds, that means we're talking there about the period. We're going to graph this period. This last piece here, T equals 0 seconds corresponds to minimum volume. It means that at time 0, we're going to have the minimum volume, and we already identified that. That's 2,200. So there's a coordinate to start with. And really, once you have one coordinate and a little bit more information, that's all you need to graph. So first of all, we're going to label our axes, and the question tells us to use V, volume in milliliters. For the dependent, and the independent is time. I'll put it down here, time. We're measuring that in seconds. So let's start with the time axis first. We know that one period takes 4 seconds, and we have to graph 2 cycles. So if we're graphing 2 cycles and one cycle is 4 seconds, we've got to get 8 seconds on here, and that'll be no problem. But I actually don't want to do count by ones because that'll crowd it in. I've got lots of space here, so I'm gonna spread it out. Actually, I'm gonna count by 0.25, I think. So I think I can fit that if I count. This is 1 second here. 1, 2, 3. I think that's what I'll do. Okay, now what about the vertical axis, the volume? Our minimum number is 2,200 and our maximum is 2,800. So I'm going to compress the graph. I'm going to put that little zigzag thing in here because I don't need the numbers 0 to 2,200 really. I'm actually going to compress it to 2,000. I'm going to start at 2,000 just to give me a little bit of space below the bottom, by bottom number. So let me put a little zigzag thing in here like this. And then I'm going to make my lower number here 2,000. And I need to get to 2,800. So I can easily count by 100s here and fit all of that in. I didn't need to go up to 3,000 or 3,200 here, but it's usually good practice to get a few numbers above and a few below your values that are in question. So we have to graph it, and we have one coordinate here, 0 and 2,200. Let's put that on the graph. There's that point. Now remember the opening slide said how important symmetry is in graphing, because I know that each cycle is 4 seconds, which means in 4 seconds I'm going to be back to my minimum volume of air again. So back at 4 seconds, I'm going to put another dot at 4 seconds and 2200 because that is one cycle. I have to graph 2 cycles, so I'm going to put another dot at 8 and 2200. Let me just label this one for you. This one is 4, 2200 because one cycle is 4 seconds, so I know I'm back there again. So speaking of symmetry, for sine and cosine waves, halfway between two minimums will be the maximum. So the maximum's got to be exactly halfway between those two. Now I know my maximum height is 2800, so it's going to be right around here somewhere. And halfway between 0 and 4 is 2. So I'm going to put a dot right there. Again, I'm going to do it again. Halfway between these two minimums is a maximum. So halfway between 4 and 8 is 6. So at 6 and 2800, I'm going to have another dot. Maximum is going to be here at 6 and 2800. I also know, so continuing with this halfway stuff, I also know that halfway between any max and any min, so halfway between 2 and 4, sorry, so somewhere here in 3, I'm going to be at the equation of the axis. I'm going to be at that horizontal line. Let's talk about that horizontal line. Where is that horizontal line? What's halfway between 2200 and 2800? So remember how to find that? You add them together and divide by 2. It's going to be 2500. So I'm going to draw a line, a horizontal line, right through here at 2500. So that is the line y equals, oops, I put it in the wrong spot. Sorry, I gotta erase that. That's better. That is y equals 2500. You could also write that line as c equals 2500. So halfway between any maximum and any minimum on a sinusoidal wave, halfway between a maximum and a minimum is the equation of the axis. So that means at 3 seconds, I'm going to have a dot right there on the equation of the axis, which is halfway. It's halfway vertically and it's halfway horizontally. So between 2800 and 2200, halfway is 2500, and halfway between 2 seconds and 4 seconds is 3 seconds. So I get a dot there. I'm also going to have one here at 1 second. This is also halfway between a max and a min, and I have other maxes and mins. So halfway between each of them, let me start with the first one. The first one I'm going to have is at 1. The next one will be at 3 on the equation of the axis. And then at 5. And halfway between the last maximum and minimum is 7 seconds. So now I have a lovely graph, lovely coordinates anyway, that I got simply from this first point and all of the information in the question. All the other points just came fluidly from that. So now I'm going to try to draw my curve. Now when you're drawing sine waves, think of the top half. Let me just draw the top half. Think of the top half of the sine wave as being concave down or part of a parabola, and then you can stop that. You could just do that first if you want. Just do this curve here. I'm pointing this out because a lot of people tend to draw straight lines, zigzags, and that's wrong. Then the bottom is concave up. So if you just think of it as drawing kind of a parabola opening up along the bottom or opening down along the top, you can have some pretty nice waves that way. And it is important that it changes concavity, that you are kind of changing the graph. You're going to talk about points of inflection next year to understand a bit more about that. So back to the question, it said draw a graph of V against T for 2 cycles. So we needed to know how long one cycle was, so that was 4 seconds. So there is our graph. Lovely. B, state the period, I better erase this. State the period, equation of the axis, amplitude, horizontal, vertical displacement for sine and for cosine. Now, all of these are exactly the same for sine and cosine except the horizontal displacement or the phase shift or the horizontal translation. That's the D value. That's the only one that's different. So for most of them, they're all the same. So I'm going to do the ones that are the same first. Let's start with, what does it have? It has the period first, okay? So the period for both of them. So we'll do for both. For both. They're both the same. The period. We've already talked about that. That's 4. It's 4 seconds. The equation, so we've got the period, the equation of the axis. So EQ apostrophe N, short for equation of the axis. We already have that. And that is a C value. That's C equals 2500. Got that. The amplitude. Remember what amplitude is? Amplitude is the positive distance from the equation of the axis to any max or min. So this space right here or this space right here. So from 2800 to 2500 or from 2200 to 2500. So our amplitude is 300. I'm just going to go back up to the period here. The period is 4 seconds, so I'm going to get a K value out of that. So from that we get a K value. K is equal to 360 divided by the period. 360 divided by 4. So our K value is a 90. That's a 90. That's the same for both. So we've got the period, equation of the axis, amplitude. The horizontal displacement is the same thing as the C value. That's the horizontal displacement. Sorry, vertical. That's a vertical displacement. Vertical displacement, not horizontal. Vertical. So that's the first part of part B now. So that's a vertical displacement, not the horizontal. Now the only thing left then is the horizontal displacement, and that's not the same for both of them. So if I was doing sine, so the first one is sine. For sine, I'm going to erase, no I won't. For sine, I'm just going to move this down here. For sine, the D value. Now remember, there's so many different ways to come up with the D value. The D value for sine is equal to the place where remember on the parent function for sine, I'll draw you a sketch here. The parent function for sine looks like this. I'm looking for this place. Where is that now? So I'm looking for where my equation of the axis hits the wave, where the equation of the axis hits the wave. That's here, 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 and here. But the wave needs to be going up. So not here, because the wave is going down. I'm going to take the first one there, that's a 1. So my D value for sine would be this value right here, because this is where my wave is going up, and my equation of the axis intersects with the wave itself. So I've got a D value of 1. And I could use other ones. I could have used this one too. I could have used 5. And I could have used 3 if I wanted to make my A value a negative. But we want to keep it easy. Now let's go to cosine. The cosine D value. Cosine D value, so the cosine parent graph looks like this. It starts at a maximum, remember? On the y-axis we're at a maximum. So we go over to our graph and we look for our first maximum. Here it is. That's our first maximum. So our phase shift is going to be 2. It's not 2800, it's 2. Because our maximum got pushed from being on the y-axis to being pushed over 2 units. So my D value for cosine, that's the second one is cosine, that's a 2. Let me just erase these graphs down here. So now we've answered everything for part B. We've stated all of those pieces. Part C, if you can see it there, write an equation for the function for each sine and cosine. How can you check these? So I have to write an equation, one for sine and one for cosine. Okay, let's start with sine. Remember what it looks like. Normally we would have f at x if we just had a function notation, but we have the questions telling us v is for volume. Volume against time is equal to, okay, start with the a value. The a value comes first. That's a 300. It's the same as our amplitude. We're not making it negative. We're not flipping anything over. Let's do sine first. Sine. Now we have a bracket, and then our k value goes first. That's a 90. Another bracket. T minus, what's the d value? For sine, it is 1. Close bracket, and then plus our c value goes at the end, 2500. That's sine. Let's do the same thing with cosine. So everything is the same except the word cos and the d value. So for cos, our d value we got was a 2. The only difference between a sine and a cosine graph is a phase shift. Sine is the same as cosine if you just move it over a bit, the parent graphs. So that's going to happen all the time that you're creating graphs. You can write in sine or cosine. And it says, how can you check these? You can check these by picking a point that we got, say this point here, subbing in, let me write it down, this 2, I would make, that's an x, the 2800 is a y, or in this case, the 2 is a t, and the 2800 is a v at t. So if I sub in a 2 for t, back in my original question here, sub in a 2, I'll get 2 minus 2, either one. And I encourage you to check both, but check either one. So if I put a 2 in here, 2 minus 2 is 0. 90 times 0 is 0. Then what is cos of 0? Cos of 0 is 1. So you're doing all these steps in order. First you sub it into the bracket. Then you multiply by whatever is your k value. Then you find cos of that number. And this, so now we're at this point where we have cos of 0. Cos of 0 is 1. So we have, that's all equal to a 1. Then the fourth thing I do is I multiply by my by my 300. So 300 times 1 is 300. And the last thing I do is I add on my final value, 2500. And the number you get here should be what the other half of your coordinate. So looking over at the coordinate, we subbed in a 2 and we got a 2800. So that's a way to check that our equation matches our graph. I'm going to have to erase all that, but that's how you check. And the last question for this example, describe how the graph and the equation would change in each case. So if a person breathes more rapidly, how is this going to change? Assume everything else is the same. They're breathing more rapidly, but nothing else is changing, meaning the maximum and the minimum volume of air is the same. But if they're breathing more rapidly, what's going to change there? So the period would change if they're breathing more rapidly. It's not going to take 4 seconds for normal breathing. It's going to take fewer seconds if they're breathing more rapidly, say 3 seconds. So the equation would change because the k value would change. And the graph would change, how the graph and the equation changes. So the graph would change because all of a sudden we have to get 1 cycle into 3 seconds. It's going to be more compressed. So describe how the graph and the equation would change. If they breathe more rapidly, the graph would change because it would be a horizontal compression. The equation would change because if our period changes, that changes the k value. What about 2? What about if the person takes bigger breaths? So now we assume that everything else is the same. The only thing changing is bigger breaths. So we're going to assume that it's still 4 seconds. We're back to 4 seconds for a breath. So 4 seconds for a breath, but they're taking bigger breaths. So that means these numbers are going to change, right? Maybe not the minimum, but the maximum if we're taking bigger breaths. The lung volume is increasing. So these numbers here. So that's the amplitude. We are going to see a the amplitude increase on the graph, we're going to see it being more stretched, coming up and down a little more, probably down a little bit more too. When you tend to take a deeper breath, you tend to exhale more as well. So, or the amplitude is going to change. That's how the graph would change. And how would the equation change? Well, if you're changing the amplitude, it means you're changing the A value of your graph. So this number would change. And assuming you take a greater inhale and a greater exhale, this number might not change. The C value might not change. That still might be halfway, but if you only breathe in more and not out more, then this number could change too. So that is how the graph and the equation would change for these scenarios. Remember, today's lesson is on problem solving, on word problems. So that's what we're trying to go through here, as to how to interpret a word problem and turn it into a graph or turn it into an equation. So let's talk about some overall tips. What we did first, read word problems one sentence at a time. Don't continue to the second until you understand the first. Very important. And most of you are probably, if you're looking at a handout or something right now, you're probably going ahead and reading it anyway. You are skipping ahead instead of doing one sentence at a time. Next is to draw pictures, diagrams, not just graphs, to get you started. A lot of times, if a common question are circular kinds of questions that are like about something that goes around, like a Ferris wheel or a tire, or sometimes you get like a piece of gum stuck on a tire or a clock. So things that go around. So if you're doing a Ferris wheel question or a clock question, draw the circle as well. So if you're doing a clock question, it might help you to just draw a clock. Or if you're doing a Ferris wheel, maybe a Ferris wheel kind of diagram, this is the ground down here, something like that. If there's a person going around the Ferris wheel, and then you might say this is the ground, this is 0 meters high, and if they give you the maximum height, you might have that there. So the diagrams, not just the graphs, can really be helpful too. Another common question, if you have something going back and forth, the sway or the swing or the motion of an object is reduced by 65%, for example. It means the amplitude of the function is reduced by 65%. So if you have a pendulum going back and forth like this, back and forth, and that swing or that sway is reduced by 65%, then the amplitude is reduced by 65, but everything else stays the same unless the question tells you. So if the question says the amplitude has changed and the period has changed, you don't assume that. So the A value would need to be multiplied by 0.35, and you're going to have a question in your homework that's going to ask you something like that. So if it's reduced by 65%, that means it's now at 35% of its original amplitude. One more, a helpful formula for these circular questions that you'll get is that circumference is pi times diameter. For something to go, like on a Ferris wheel, all the way around the outside, you are looking usually at the distance traveled around the outside, and that's the circumference, the distance traveled around a circle. So circumference equals pi times diameter. That's it. Word problems, tough. That's why they're usually at the end of every topic in math, because you need to pull together everything you've learned so that you can tackle these word problems, which is really what a lot of our math is getting us ready for, is real world problems.